two-step process. In the first step, we shall have to establish that the association that we get to see is a valid association, and then once we are sure that the association is valid, then we can move from there to a causal inference. Validity of association is contingent upon achieving three things. We should be ruling out chance, that chance occurrence could be a factor that can explain the association. We should eliminate biases even before we plan the study or at the stage of planning of the study. And we shall have to control for confounding variables, the role of confounding variables. Once these three things are achieved, then we are in a position to evaluate causality or causal, whether that linkage is one of causal or not. So the first item in the agenda is that we should rule out chance as the association between the two variables, that is exposure and the outcome variables. In order to do that, we'll have to set up hypothesis. And in order to set up hypothesis, we start with a theory or thesis, and then the theory will determine our null hypothesis or our alternative hypothesis. And here I'm going to give you an example. Say, for example, we are interested to study the association between environmental tobacco smoke and the occurrence of lung cancer. We believe, or the theory is this, that environmental tobacco smoke can cause lung cancer. The first thing that we have to show is this, that there is a valid association between environmental tobacco smoke exposure and lung cancer. Environmental tobacco smoke exposure is measured using urine cotinine values. So we state the hypothesis as follows, that amongst people with lung cancer, we shall find higher levels of urine cotinine. This is known as an alternative hypothesis. The null hypothesis would state that urine cotinine levels amongst people with and without lung cancer will be similar. So in hypothesis testing, we test whether the null hypothesis can be rejected. So in order to do that, we set up a 2x2 table. And in the 2x2 table, in this particular instance, the null hypothesis is stated as follows, that environmental tobacco smoke is unrelated to chronic lung disease or lung cancer in this particular case. So we'll say environmental tobacco smoke exposure as measured using urine cotinine levels will be very similar for people with and without lung cancer. And in this 2x2 table, our findings, based on our findings of actually conducting the study, we can either reject the null hypothesis or we will not reject the null hypothesis. In that case, the technical term is that we fail to reject the null hypothesis. If we falsely reject the null hypothesis, then we commit an error which is known as type 1 error, also known as alpha error. If we falsely reject the type, if we falsely fail to reject the null hypothesis, in other words, we reject the null hypothesis where the null hypothesis actually, we cannot reject the null hypothesis, but the null hypothesis is actually false. That too is an error, and that is known as type 2 error. As I said, type 1 error is the error of falsely rejecting the null, also known as alpha error, and this probability should be set before the study, and it is usually set at 0.05 or 5%. Type 2 error, on the other hand, is the error that we commit if we falsely fail to reject the null hypothesis. This is also known as beta error, and it is also known as beta error, and the beta error is usually set at 10% or 20%. So the beta error is usually given a value of p of 0.20 or 0.10. What is the power of a study? The power of a study is the probability of rejecting the null when a null is false. So if we go back to our original 2x2 table, you see that when the null is false and we reject the null hypothesis, we actually are correct. And the probability of being correct is what is known as the power of a study. So of all the possibilities that a null is false, how much were we able to correctly predict that the null was false? So that's the power of the study. And the power of the study, of course, is again dependent on the type 2 error, and therefore power of the study is given as 1 minus beta error probability. And all of these things, that is alpha error, the beta error, and the effect size estimates, are used for sample size calculation. So the sample size can be estimated prior to beginning a study. And for the sample size, we will need the prevalence of the exposure for an exposure outcome kind of study. the effect size that we shall consider as to be important, and the levels of the alpha and beta errors. So let's take a look at a very quick way of conducting sample size calculations. And here is a website known as openepi.com. And in the openepi.com, there is a table that you will need to fill in order to calculate your sample size. So you click here to enter new data, and when you enter new data, you give that the alpha error at 5%. So the 1 minus alpha is usually 95%. Your power, it's usually 80%. Remember, the beta error was 20%. And the ratio of case to control, in this particular case, we are going to put together a case control study, and the ratio of cases to controls is 1.0%. And in this particular situation, let's say we would expect that only 40% of controls will be exposed to the area of interest, say environmental tobacco smoke, and we say that 40% of our controls will be exposed to environmental tobacco smoke. If we give them these 4 parameters, and then if we ask them to calculate the study, calculate the sample size, we need one more thing, and that is the odds ratio. In this case, let's say we believe that an odds ratio of 2.5 times is going to be really important. We'll say that people that the cases are 2.5 times more likely to be exposed to environmental tobacco smoke than the controls. When we do this and hit calculate, the program calculates for us the sample size, and you can see that there are many different ways in which this is calculated. And the total sample size for the different studies don't vary much. It varies between 154 to the lowest and 170 to the highest. So let's come back to the thing. So these are the ways in which we can control for the play of chance. That is, we set up the alpha error, we set up the beta error probability, we set up the sample size, and once we are satisfied with the sample size, and we conduct the study with a sufficient sample size, we can ensure that the play of chance will be minimized. The second thing, which is very important, is to know about bias. And bias refers to the process of a systematic error that can occur in the conduct of the study, either in the form of planning the study or during the process of data collection. And there are a couple of ways in which biases occur in studies. One is known as selection bias, the other is known as response bias. Bias can also be random or non-random. Random bias basically means that the similar kind of bias occurs across the board, which means, for example, in a case control study situation, the same type of bias will occur for both the cases and controls. Non-random bias refers to a situation where, say, the comparable groups data are collected from them differently. Either they were selected differently, or when they respond to certain questionnaires, those question responses are quite different. So that's about biases. Now, selection bias is one where the participants in the comparison groups are selected differently. Say, for example, in a case and control study on the association between environmental tobacco smoke and lung cancer, the cases and controls are selected quite differently from 2 different situations. That is, maybe the cases or patients with lung cancer are selected from cancer ward, but the controls or people who do not have lung cancer are selected from general population. So that is an example of a selection bias that can occur. Similarly, for cohort studies, the exposed and the non-exposed cohorts that are assembled differently. And therefore, when that happens, we do not know what will be the direction of the effect estimate. For example, in case of a random bias, we know that the effect estimate that we are going to observe, will be away from will be closer to the null from the true effect size. Here, we have no way of knowing this because that's a non-random bias. So, reviewing once more the non-random bias. Non-random bias refers to So that's about the selection bias. The second thing is about response bias. In response bias, we have the situation where the members of the comparison groups provide us with very different levels of information across the comparison groups. Say, for example, in a case control study, the cases and controls provide different kinds of information. In other words, the cases may provide truer information, whereas the controls may provide false information, or the other way around. For example, in a lung cancer and exposure to environmental tobacco smoke, people who know that they have got lung cancer may provide a greater level of recollection about their exposure to invulnerable tobacco smoke than the controls. And as we discussed before, random bias is the one where participants in both arms of the comparison suffer quite equally in terms of the bias. So that does not really matter. And therefore, you know that the effect estimate is drawn towards null compared to what would have happened if they were, if the bias were not to exist. A non-random bias, of course, is one where we do not know where the effect estimate is going to lie compared to the true ones. The last thing that we're going to study here is what is known as confounding variable. In a confounding variable, the confounding variable actually is an alternative explanation of the association between the exposure variable and the health effect. For example, in the invulnerable tobacco smoke and lung cancer study, a potential confounding variable would be active smoking status, because active smoking is associated both with the health effect, which is lung cancer, but active smoking is also associated with passive smoking, because in this particular example, the exposure to passive smoking or invulnerable tobacco smoke is measured using urine cotinine levels. And urine cotinine levels are also influenced by active smoking, and therefore there is a close correlation between active smoking and passive smoking in this particular example. And because active smoking is also associated with the health effect under study, which is lung cancer, therefore such a variable can confound the association between invulnerable tobacco smoke and any particular health effect that we get to see. So that is the nature of a confounding variable. A confounding variable is independently associated both with the exposure variable as well as the outcome variable, but the confounding variable does not come in the causal pathway that may link the exposure variable and an outcome variable or the health effect. So this is an important point to understand. How do we assess confounding variable? There are usually three ways in which confounding variable can be assessed. Now, another issue that needs to be understood about confounding variable is this: that confounding variables are essentially conceptually determined. In other words, if you would like to know whether a particular variable is a confounding variable or not in the association between an exposure and an outcome, one needs to consider whether there are theoretical issues that need to be considered. For example, in the example of invulnerable tobacco smoke study, where invulnerable tobacco smoke is the exposure and lung cancer is the outcome, active smoking is a confounding variable because there are known associations between active smoking and lung cancer. Similarly, for example, if we knew that women are more prone to invulnerable tobacco smoke, but they are less likely to develop lung cancer, again, that would be another example of a confounding variable. And there are three ways in which this is done. One is an elimination of the confounding variable. So we should eliminate participants who may have one or other who may have got one or other kind of be a confounder. For example, in an invulnerable tobacco smoke and lung cancer study, we would confine the study only to, say, for example, women who are non-smokers. So that's an example of this. And the problem, of course, with elimination is that we end up with very low sample size, and therefore the studies are underpowered. Matching is one where we match participants. So we take women, for example, say 50 years of age, and we match the cases and controls along those lines, say, for example. So something like this. Again, too tight matching can lead to erroneous results, and particularly, again, will result in low power. That will happen as a result of this. The third strategy for controlling for confounding is to use multivariate analysis, and this is done after data are collected on a number of potential confounding variables, and these are adjusted in the form of a statistical data analysis where these are conducted. So this provides you with a very rapid tour of the three more important things that we must consider for establishment of valid association. That is the role of chance, and we should rule out chance. We should eliminate any kind of bias at the beginning of the study, and we should control for confounding in a number of different ways. And after we have achieved these three things, that is, we have ruled out chance, eliminated biases, and control for confounding, we should start evaluating causality, which is going to be the focus of our next presentation. So Thank you for paying attention to this. Let's move on to the third lecture where we will look at causal association. Thank you.